In this video, we'll be reviewing Chapter 4 in preparation for the final test. And so, again, just looking at the table of contents of the chapter outline. Spring rates, we talked very briefly about structures as springs having a force deflection ratio. And that idea came in a much bigger way when we were understanding springs have energies and moving on to Castiglione. Deflection in tension, compression, and torsion, we'll see that. That is fair game. I won't have anything directly on spring rates on the test. Deflections due to bending, we will definitely have that involving both superposition and singularity. Strain energy, which introduces Castiglione, and Castiglione of curve members, and Castiglione indeterminate. We will have all of that. Compression members, we talked about Euler buckling and Johnson buckling, so that will definitely be fair game for the test. Let's see, elastic stability we just talked about. There won't be anything on the test on that. We talked about shock and impact, but neither of those will be on the test. So spring rate, force over deflection, interesting idea. That's not going to be directly on the test. Deflection due to tension, compression, and torsion. These are just very well-known equations. Copy them to the sheet. Deflection for tension compression is FL over AE. Angular deflection and torsion, TL over GJ. Nothing terribly interesting there. Beam deflections, had a discussion on the relationship between curvature and moment, which finally leads to the key equations that we would work with. Loading being a fourth derivative of the shape, shear a third derivative, moment is related to the second derivative of the shape, slope is the first derivative of the shape, and y is the shape. And so we have drawn shear, moment, slope, and deflection diagrams in the pass-through strength of materials. This example uses strength of materials techniques more than anything. We are not going to use pure strength of materials techniques. We certainly talked about superposition, where we might have a beam that has composite loading. This loading can be described by two simpler beam loading systems. One, a simply supported beam with uniform load all the way across, but no point load, and then a different beam which is simply supported with a point load that's not located in the center. If we can find those two solutions in a reference somewhere, then we can use superposition to combine those two by finding the equations that are true for each of the simpler systems and putting them together. About the only thing that is interesting is how to put them together, and you might remember that diagram that I drew for you. I don't have any samples of that in the notes, but it basically helps you decide which equation to use in this region and which equations to use in this region. You'll find that diagram in your notes. If you have any questions, ask me. So a couple of superposition examples. Okay, singularity. Let's see, I guess these are my chapter 4 notes, and we do have the singularity definitions. Basically, the singularity functions, what I need to remind you is what some of you forgot on the second test, is that this x minus a to the minus 2 quantity, or any of these x minus a terms, every one of them returns 0 if x is less than a. Every one of them. And so and that's the whole point. They're turned off until the point where they're supposed to be turned on. And some of you in your boundary conditions, when you plugged in a 0, you said this returns a minus a, especially when we got into the higher power ones. When you plugged in x equals 0, you said this returned a minus a to a certain power, and that's definitely not true. Okay, so we have our singularity functions, and then we typically apply them by taking some kind of a structure and working from x equals 0 at one end or the other. Probably, I don't know, this one might actually be easier to start with x being measured from the right hand end, because then we could wait to turn on this load. With x starting from the left hand end, we'll turn this load on immediately, but we don't have a means of turning it off, so what we'll have to do is turn on a negative load companion to this one, and that's what we'll see in the loading function. We will have in the loading function an R1. Now, eventually, before we finish the problem, we really must fill in the statically determinate value of R1. It's okay to start it this way, but at some point we have to do this right here. That from start R1 from statics, WA over 2L, 2L minus A, whatever the statics happen to be, we have to do that. We don't have a complete expression for the deflection. So in this one, we have a point load, R1, that's positive. We had a distributed load W, which makes it an X minus 0 to the 0 power. And when we have things that turn on at 0, we don't even really need singularity functions for those kind of things. This is still written as a singularity function, but this could just be written as a pure X minus 1, no singularity. A pure, or X to the minus 1 power, no singularity. X to the 0 power. No singularity actually required here, but it's also okay to write it as a singularity function. Now, this distributed load is negative, therefore down, but notice we have another distributed load that's positive, therefore up, and it turns on at A, and what it does is when we turn this load on, it continues forever. So we need a reversing load to turn off this load. There it is. Then finally we have the reaction at the other end. It happens at X equal L. So this is an X minus L singularity function. Once we have the singularity function and we do the statics so that we don't actually have to write it in yet, just sometime before the end we have to make this substitution. We can then integrate Q, but the integration process is really just a promotion process with the singularity functions. So I promote every one of these powers by 1. V is the previous equation, every power increased by 1. And we do that until we go from a 1 to a 2, because then we have to divide by a 2. So we write the moment equation. We integrate again, and we get the slope equation. We integrate again, and we get the deflection equation. But our statics is sort of pooped out on taking care of constants of integration, because by the time we get to the slope, we need another C1. And the deflection is going to have, when we integrate the C1, we'll get a C1x, followed by a C2. And so, and then we have to use proper boundary conditions. It is certainly fine to say that the deflection at A, or at X equals 0, is 0, and the deflection at X equal L is 0. That's because we have a simply supported beam. If we had a cantilever beam, we could certainly not say that the deflection at the free end is 0. Cantilever beam, we would say deflection at the wall is 0 and slope at the wall is 0. So we have to apply the right kind of boundary conditions. So this is a singularity example. You can take a closer look at that one. Strain energy, we defined for the various systems. We're not really going to worry about that too much because we have a better equation to use. Okay, strain energy of beams was developed. Okay, we could then calculate strain energy, but that's not where we're wanting to go. We're wanting to go to Castigliano's theorem. We have read this paragraph about 37 times. I've only put a subtle twist on this thing to account for indeterminate structures. Okay, because Castigliano's theorem says that when forces act on an elastic system subject to small displacements, the displacement corresponding to any force in the direction of the force is equal to the partial derivative. So it says deflection equals partial derivative of strain energy. What I'd rather say is when we take the partial derivative with respect to strain energy, we now have an equation that relates deflection to that original force. And that's a little bit of broader interpretation because that means we can either use the equation to solve for the deflection, or if we know the force, or we can use it to solve for the force if we know the deflection, and that's what lets us handle indeterminate problems. Okay, this early statement says we must have a force there of the right kind at the right place if we want to know the deflection at a certain place. That brings along the idea of the fictitious force or dummy force that we must later set equal to 0 to get the proper deflection. Scrolling through, Um, let's see. This is where it talks about applying a dummy load, and then we have examples. This is what says we can do the partial derivatives early, which then if we have dummy loads, let's set q equals 0 early. And so this is the form that we're going to use more often than not. An example of two different I values, so the EI changes. This is an example that's just not a simple straight beam, and that we have to account for all of the kinds of energy in this segment, all of the kinds of energy in that segment, and all of the kinds of energy in this segment. Quick reminder, this force causes one direction of bending in this segment. This force causes outward bending of this section in the direction of F, but it also causes a twist or a torsion in this section. This load causes a downward bending of this member, and it causes an outward bending of this member. It also causes axial tension of this member, which is pretty small, but I think it was incorporated into this problem. So you go through and you integrate all of those various pieces, add them together, and we can get the deflection of this point on this structure in the direction of the load. Deflection of curve members. If it is a thick curve member, then we'll use the eccentricity form of curve beams that we used back in chapter 3 to calculate deflection. So we'll use an eccentricity value both for stresses and deflections. If it is a thin curve member, where the radius of the curvature is much larger by a factor of 10 than the h of the member, where h would be measured, well, h is shown right here. So r over h greater than 10, we can use the standard straight beam bending deflection energy equation, and it gives a very good approximation. Okay, and let's see, this one would be a axial deflection piece. And so what's the real trick of curved beams? Understanding that this force is going to cause a force here, which can be divided into a shearing type component, a axial type component, and a bending moment, and realizing that these components change as the angle theta changes. So we need to be able to write this force as a function of theta, this force is a function of theta, that moment is a function of theta, and if we had out of plane loading, we would also have to be able to write torsion as a function of theta. I will leave curved Castiglione as fair game for the test. And what the author has done right here is for this problem, given you the values of force, the two forces, and the moment as functions of theta. This is an example that has an out-of-plane loading for the curved ring, so we will certainly have torsion at every point within the cross-section, and we will have bending. And one of the things that's needed when we're doing circular curved beams is because the integrals will involve, or the forces will involve sines and cosines, the partials will involve sines and cosines, so we'll have products of sines and cosines that have to be integrated. So here's the definition of sine squared, cosine squared, and the sine cosine integrals. And for this particular problem, here's the bending moment as a function of theta, and here's the torsional moment as a function of theta. These energies can be written up. This looks like a very thin beam as compared to radius compared to height, so we could probably use thin beam technology on this. And so then we have an example of a curved beam, and what's especially interesting about this example, I think, is not only do we have bending moments that would be changing as a function of theta, but EI, particularly I, the moment of inertia, would also be changing as a function of theta. So you'd have to keep an eye on that. Yes, that's right. Cross-sectional, okay, in this form, because it is clearly a thick beam, yes, I is changing, but the easier version is area is changing. So we would need to write area as a function of theta. Okay, statically indeterminate problems in Castiglione, they're really no different when we remember that what Castiglione gives us is not an equation for solving deflection, although it sort of gives that. It gives us an equation that relates the deflection to the force through an equation. And that equation can be used to solve for whatever we want. So if we don't know the force, because it's indeterminate and we can't get it through statics, then we can use Castiglione to write an equation that relates the deflection that we already know to the force, which will allow us to solve for the force. That's what all of this explains. So we have a cantilevered beam with a simple support, clearly indeterminate. Okay, when we write out the reactions at the cantilevered end and at the simply supported end, we have 3 reactions, and that's one more reaction than we can handle through our statics. So we could treat any one of these as the indeterminate reaction, or therefore an indeterminate force, and use Castiglione to solve for the reaction force or moment. The easiest one, of course, is R2, because we can then measure x from the left and look left as we write our terms, and we don't even have to do the statics of these. But there are certainly other ways we can do it, and in my samples I did both the easy way where R2 was treated as the unknown, and I did the harder way where M1 was treated as the unknown, and I measured x from the left and I looked left. So I did it the hardest way and the easiest way on those videos in the handout that I gave you. That's Castiglione. Again, summarizing Castiglione. Castiglione says using energy, we can write an equation between force and deflection. In the most simple method, we have a force there, and we use Castiglione to calculate the deflection at that same point. First complication is we have no load there, so we simply place a dummy load there, solve the problem, and set the dummy load equal to 0, and we get the deflection at a point where there was no load, or where there was a load of size 0 applied. Next method then is indeterminate structures, where we replace a support with an unknown load and use Castiglione to solve for the known load, and then final complication would be curved beams. Okay, compression members is buckling. We have different end fixities or end conditions when we're talking about buckling that give us different C values. These are the theoretical C values. There's a table in just a moment that shows the practical or suggested C values. We have the Euler equations or definitions for peak critical, the critical load that will cause this thing to collapse abruptly. Moment of inertia defined in terms of radius of gyration, and radius of gyration in just a moment will be used with L to calculate a thing called the slenderness ratio. So here's a redefinition of P critical over area in terms of this thing called L over K, quantity squared, and L over K, where it's the same K right here, is called the slenderness ratio. We have theoretical values of end fixities or end conditions. We have conservative values if we're really unsure, and we have recommended values, especially for the fixed and rounded. We're not going to use the 2s and 4s. We don't trust our end conditions well enough to do that, but we'll give them just a little bit of a benefit and use 1.2. This is a curve of Euler, and if we were to follow the Euler curve, it says that the critical load increases pretty much to infinity as our beam gets shorter and shorter and shorter. But it turns out that the nature of buckling changes at some point, and we know that we're going to fail in compression by yielding. For the ultimate short structure, it won't really buckle, it will fail by yielding, and so this parabolic curve here brings in the idea of a combined failure mode of both yield and buckle. And so we'll have Euler if we're a very long beam, and we'll have Johnson if we're a very short beam. Of course, we have to determine where the changeover point is. This is the critical point that tells us where the changeover point is. This quantity is the same units as an L over K value. We compute the right-hand side, and we call that the L over K critical value. We compare the critical value to the L over K of our actual structure. If our structure is longer than this L over K, then we have an Euler beam. If our structure's L over K is shorter, then we have a Johnson beam. Once we determine that we have a Johnson beam, of course, we need to know the critical loading formula. So this is the critical loading formula for the Johnson beam. We talked briefly about columns with eccentric loading, but I didn't give you any homework on it. We're not going to have that on the test because it involves solving this secant equation, which is nonlinear and non-isolatable in our load P, since it appears on both sides, and on one side it appears within the secant. Short strata compression members also, I didn't give you a homework assignment on it, but just as a general structure, realizing that this load being offset by a distance E will cause a bending moment. This is nothing but combined bending and compression because of this loading. And even though this topic isn't something I would say I have given you homework on, the idea of combined loads, both bending and axial compression, we've had from the very beginning. So in that sense, this would be a fair game kind of problem where we would have both a P over A, axial compression or tension loading, and a bending loading. Nothing really special about that. The rest of this chapter we talked about briefly, but there was no homework assigned and it won't be on the test. So that ends this video.